Welcome everyone to our video on a review of acids and bases. In this video, we will review the Arrhenius theory of acids and bases, learn how to write the ionization equations for strong acids and strong bases, and learn some basic calculations going in between pH and hydrogen ion concentration and pOH and hydroxide ion concentration. On a macroscopic level, acids are chemicals which are being grouped together historically by some similar properties. Acids typically have a sour taste, they are corrosive, and they have a chemical property in that they neutralize the properties of chemicals called bases. On the macroscopic level, bases also are grouped together by some similar properties. Bases often have a bitter taste, so think leafy green vegetables. Bases are often very slippery if you feel them to the touch. And bases are corrosive as well. Many strong cleaners are bases. For example, Drano is sodium hydroxide, and their corrosive properties are used to eat away at substances stuck to typically metal in our kitchen appliances or in our drains. And bases have a property in that they can neutralize the chemical properties of acids. In previous grades, you've been introduced to the Arrhenius theory of acids. This theory defines acids in terms of what happens when that substance is dissolved in water. And specifically, an acid is a substance which produces hydrogen ions when it is dissolved in water. The equation that we see here on the screen is referred to as an ionization equation for an acid, in which the left side of the equation shows the unionized molecule, and the right-hand side of the equation shows our ionized acid, hydrogen ions, and whatever the anion is. The Arrhenius theory has a similar definition for bases. A base is a substance which produces hydroxide ions when dissolved in water. This dissociation equation shows the production of the hydroxide ions from the undissociated base. So according to the Arrhenius theory, acids and bases occur in aqueous solutions when they are dissolved in water. And it is two specific chemicals which give these substances their properties. It is the hydrogen ions, which gives a substance its acidity, and the presence of hydroxide ions, which gives a substance its basicity. Let's look at the ionization equations for two common acids. At the top, we have hydrochloric acid. We see that in the balanced chemical equation, every one molecule of hydrochloric acid produces one hydrogen ion and one chloride ion. It's a 1-to-1 ratio between the unionized acid and the quantity of hydrogen ions. This is what's referred to as a monoprotic acid. Sulfuric acid is a diprotic acid, which refers to the fact that the unionized acid produces two hydrogen ions. In every one molecule of H2SO4, there are two hydrogens, and those two hydrogens are released when it dissolves in water. An acid which produces more than one hydrogen ion per molecule of acid is referred in general as a polyprotic acid. You may have heard the terms strong acid and weak acid before. We define the strong acid versus weak acid based upon what percentage of those molecules ionize in water. A strong acid ionizes completely. A weak acid only ionizes partially. This is an incomplete reaction, where less than 50% of the molecules release their hydrogen ions when they're dissolved in water. Many of the acids which we use in chemistry class are strong acids: hydrochloric acid, sulfuric acid, nitric acid. Similarly, you're probably familiar with many of the strong bases. For example, the group 1 hydroxides, sodium hydroxide, potassium hydroxide, lithium hydroxide, are all examples of strong bases. Weak acids often show up in food products. So for example, acetic acid is the acid present in vinegar. And we have citric acid and ascorbic acid, which are found in many fruits. You might not be as familiar with some of the names of the weak bases, but they are often organic molecules, carbon-based molecules, which contain some nitrogen as well. The one that you might be familiar with is ammonia, NH3. To calculate what percentage of the acid ionizes, we use the percent ionization equation. In this equation, we take the concentration of hydrogen ions once the acid has ionized and divide it by the concentration of the unionized acid before the reaction began. And we express it as a percentage. We have a similar equation for bases, in which case the numerator is just the concentration of hydroxide ions. This equation is actually the same equation as you may have learned previously as expressing with percent reaction, because this tells us how complete or incomplete the ionization reaction is. Let's look at the ionization process from a particle level. If we place 5 molecules of hydrogen chloride in water, being a strong acid, 100% of them will dissociate. So we get a 1-to-1 ratio between the number of molecules that we placed in and the number of hydrogen ions which are now present in water. If we look at a weak acid, like acetic acid, CH3COOH, it ionizes incompletely. Less than 50% of the molecules release their hydrogen ions. Since it is the hydrogen ions which gives an acid its acidic property, fewer hydrogen ions means that substance is going to have properties that are weaker or less acidic than a strong acid. And this is why weak acids often show up in food products. Maybe they'll sting a bit if you get some on a cut, but you can still have them safely in a food product to preserve a substance or to add flavor. You are already familiar with the pH scale, which gives us a sense of how acidic or basic a substance is. On this scale, a pH of 7 is a neutral substance, neither acidic nor basic. As we get lower and lower numbers, those substances become more and more acidic, and higher numbers become more basic. This scale is typically presented on a 14-point scale, but that is only because many of the common items that you're familiar with fall within that 14-point range. The pH scale is a logarithmic scale, which means that every step is a factor of 10 in terms of how acidic that substance is, or the concentration of hydrogen ions. So moving from 3 to 2, vinegar to a lemon is 10 times more acidic than vinegar. And if we compare vinegar to stomach acid, 2 steps on the pH scale, means that stomach acid is 100 times more acidic than vinegar. The pH scale is specifically based upon the concentration or molarity of hydrogen ions in that solution. To calculate pH, we take the negative log base 10 of the hydrogen ion concentration. Recall that when you see a square bracket around a chemical, that is always referring to the amount concentration or molarity of that chemical. On all scientific calculators, the default log button is a log base 10. So when you're calculating pH, you're just using that log button on your calculator. We should also be able to go in reverse and, knowing the pH, calculate the hydrogen ion concentration. In this case, the hydrogen ion concentration in moles per liter is 10 to the negative pH. The best button to use on your calculator to calculate this is the second function log button, which is typically 10 to the power of x. So you just press that second function button and the log button, and then type in negative and whatever your pH is. Although the pH scale is the default scale that we use for talking about acids and bases, there is also a pOH scale, which is based upon the concentration of hydroxide ions. You can see the calculations at the bottom here are exactly the same, but rather than talking about hydrogen ion concentrations, we are now looking at hydroxide ion concentrations. And the way the scale works is that the numbers everything is reversed. It's still a log base 10 scale, but low numbers, less than 7, refer to basic substances, and pOH values of higher than 7 are acidic substances. So this wraps up our review and introduction to acids and bases.